Good evening.
Good evening. Thank you.
Many moons ago, I talked to you about the beginning of everything. This is the end of that story, the end of everything. As you can see from the subtitle, I'm talking about the fate of the Earth, the fate of the Sun and the solar system, the fate of the galaxy, and ultimately the fate of the universe. So we'll be looking at everything in the future from not quite tomorrow till the end of time. So in other words, we're going to eternity and beyond. So I'll give a little bit of a prologue, and then we'll be talking about the future, and I'll be doing this in strict chronological order, but to start with, it'll be the future of the Earth, the Sun, and the solar system. As we go further into the future, the far future, we'll be looking at the fate of stars and galaxies. And before we finish, we'll be looking at the far, 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 far future and the ultimate fate of the universe. And if that's far too depressing, I'll finish with a little bit of an epilogue that hopefully will cheer people up just a little bit. So, I think it was about 4 years ago I gave you the beginning of everything. So I'm not going to recap that, just to remind you that as far as we understand it, at the moment, the Big Bang occurred 13.8 billion years ago. The universe was created. It made a lot of hydrogen, a little bit of helium as well, but a lot of hydrogen, and that hydrogen ultimately made the stars and the galaxies and us in due course. It took about 3 minutes to make this, but it's going to take a lot longer for it to come to an end. In order to keep track of where we are in time, I'm using this timeline at the top. I'm not talking about years or thousands of years into the future. We're going to use a logarithmic scale, otherwise it just gets crazy to try and look at events in the far future. So each small box there in the top represents a time 10 times further into the future. Rather than do a linear scale, we're doing a logarithmic scale. So in other words, we're going to be looking, for instance, 10 to the power 3. If the 3 is lit up, that means we're looking 10 to the power 3 or 1,000 years into the future. If we keep on going, when we get to 6, 10 to the 6 is 1,000,000 years into the future, and so on and so on. 7, 8, 9, 1,000,000,000 years into the future, 10, 11, 12, 1,000,000,000,000 years into the future. So that red rectangle is going to move across the timeline so that we can sort of keep track of where we are. And I'll be talking about probably thousands and millions and billions, but eventually we're just going to have to talk about 10 to the power a big number, because we run out of adjectives to describe just how big these numbers are. Could I, before I move any further, acknowledge the fact that a paper by Adams and Laughlin from 1997 actually lays out calculations of the timelines on which various physical phenomena are likely to occur, and I've used that paper as a guideline effectively to get my slides in the right order. In other words, I'm moving continuously into the future, even if that means jumping around from the Earth to the Sun to the galaxy back to the Earth, who knows. I'm trying to keep things in a time order. So I'm not going to be talking 10 years into the future or 100 years into the future. Let's assume we get climate change under control. Let's assume we don't have an all-out nuclear war. The first interesting thing that would happen, perhaps, is 1,000 years into the future. We know at the moment that the Earth's spin is slowing down. The Earth's day is lengthening because of the pull of the moon. At the moment, we add a leap second every few years. We haven't done for a long time, but every once in a while, we add a leap second to keep the rotation of the Earth synchronized with our clocks, or I guess the other way around, our clocks synchronized with the rotation of the Earth. In 1,000 years, the Earth will have continued to slow down to the point where instead of adding a leap second every few years, we have to add a leap second every few weeks in order to keep our clocks synchronized with the rotation of the Earth. The 4 years into the future, who knows what will happen? It might be that some stars have gone supernova, but that's, well, we can't really tell. There are certain things that we know are going to happen. Some stars are going to go supernova, and they might do in 10,000 years or so, but we can't predict that with any sort of certainty. But on the same time scale of 10 to the 4 years, we do know that things are going to change here on Earth. The Earth's axis points to a particular point on the sky, which isn't fixed, looks fixed at the moment, just next door to Polaris, but the Earth's axis is actually precessing with a period of 26,000 years. So you can see the Earth's axis sweeps out a circle on the sky. It's a fairly big circle. At the moment, the Earth's axis is pointing close to what we now call the pole star, for obvious reasons, close to Polaris. But in another 10 to 12,000 years, the Earth's axis will be pointing the other way. In other words, it'll be roughly halfway around this circle, and it'll be pointing close to Vega, which means our pole star then will be Vega, which makes it very easy for Boy Scouts to point out which way is north, because one of the brightest stars in the sky will always be pointing north, making it a lot easier, especially for those people who believe that Polaris is a really bright star and are disappointed to find it's actually not that bright. So apart from helping Boy Scouts, what difference does it make if the pole star changes? Well, there is actually one consequence, and that is if we think of where we are at the moment, we are closest to the sun, perihelion, in January, in northern winter. So even though we're closer to the sun, because we're tilted away from the sun, we get winter when we're closest to the sun. But when the Earth's axis is pointing in the other direction at Vega, we'll have this situation that we're closer to the sun during northern summer, which means the seasons are going to be just a little bit more exaggerated. Rather than the distance to the sun mitigating the seasons, it'll actually exaggerate the seasons. So there will be variations in the Earth's climate, and some of those variations to the Earth's climate, not necessarily. These will be a function of the way the Earth is spinning and the way the Earth is going around the sun. And any variation in the Earth's climate, which is a function of the Earth's spin or the Earth's orbit, they're all collectively called Milankovitch cycles, and I'll be coming back to that in a little while. 10 to the 5 years, now we're talking 100,000 years into the future. Voyager, or the Voyagers I should say, as there's two of them, launched in the 1970s, will be passing nearby stars. So perhaps you remember back in 19... the two Voyagers were launched. One went past Jupiter, Saturn, and the other went past Jupiter, Saturn, Uranus, and Neptune. And they are both now leaving the system. Having got gravity assists from various large planets, they're now going fast enough to leave the solar system. And it's calculated that in about 30, 40, maybe a little bit more, 1,000 years, they will be passing through other solar systems. So at the top there, Voyager 1 is on its way to the star Gliese 445, and on this sort of timescale, it should pass through that solar system. Voyager 2 is heading off in a different direction, and that's going to pass very close to the star, through the star system, Ross 248. Pioneer 10 and 11 are also on this diagram. They were actually launched earlier than the Voyagers, but they're not traveling as fast, so they're not going to get to the stars any earlier than the Voyagers are going to reach the nearest stars. Pioneer 10 is heading off on the right-hand side of this diagram towards the star Aldebaran, and Pioneer 11 is heading off in the left-hand direction of this diagram, off towards the center of the galaxy. Still on a timescale of 10 to the 5, 100,000 years into the future, we know from the Earth's fossil records and other records that we have had ice ages. There have been cycles of ice ages and interglacial or warm periods between the ice ages, and these have tended to occur, roughly speaking, on a 100,000 year timescale. Earth entered an interglacial, a warm period, relatively recently, so we can predict with some certainty that we're going to be in another ice age in 100,000 years' time. This is a consequence of the way the Earth is orbiting the Sun, and is another manifestation of what we're calling Milankovitch cycles. If anybody's interested in these, you can go and Google that and find all sorts of interesting information about them. Still on 10 to the 5 years, we're now 100,000 years into the future. The moon is still tugging on the Earth because of the tides and slowing the Earth down. So remember, we said at the moment leap seconds are added every few years. We said earlier we'd need to add them every few weeks. By this point, we would need to add leap seconds every day to keep our clocks synchronized with the rotation of the Earth. In other words, at this point, the rotation period of the Earth wouldn't be 24 hours relative to the Sun. It would be 24 hours and a second. And therefore, we would have to add that second every day to keep clocks synchronized with the Earth. still 10 to the 5 years into the future. I said earlier, we don't know when supernovae are going to go off, but this is a pretty good candidate for what may be first. Eta Carina. This is what it looks like at the moment. This is a Hubble Space Telescope image of Eta Carina. And you can see there's an awful lot of gas and other debris around it. That's because this particular star appears to be very unstable. And for thousands of years, it's been sloughing off its outer atmosphere and producing these various structures that we can see there. So it's been unstable enough not to be able to hold on to some of its outer atmosphere, and hence it's seeding into stellar space with this material. And we think that's an early sign of the fact that this star is getting to the end of its life and is definitely a candidate for supernova on these sorts of timescales. It may be beaten to the punch by other giant stars that are around and also getting towards the end of their lives, like Antares, or indeed Betelgeuse is also another candidate. So this is a photograph, an astrophoto taken by somebody in Prague, where they've taken a rather nice image of Orion behind this particular observatory, but then they've digitally enhanced, if you like, what Betelgeuse might look like if it goes supernova. In other words, it'll completely ruin the constellation of Orion, and it will produce a star which is visible not only as a very bright star during the night, it will probably be visible during the day as well. So again, we don't know whether Betelgeuse or Antares or Eta Carina is going to go first. It's probably going to be one of those. It might conceivably be another. But even watching these stars very carefully, it's very difficult to predict exactly when they are going to go. But it's not necessarily just supernova that we have to worry about, in the sense of, well, Betelgeuse is far enough away that if it goes supernova, it's going to be quite bright, but not a threat to Earth. But there are some stars, for instance, Wolf-Rayet 104, even though it's 7,000 light years away, that's some 10 times further away than Betelgeuse, this could be a threat when it dies. Some stars, such as this one, might produce a radiation burst when they die that's even more powerful than a supernova, because they produce jets, which then beam the radiation in particular directions. That's a consequence of the way these systems are rotating. Highly rotational systems can produce jets via a mechanism that we don't fully understand. But Wolf-Rayet stars, again, are quite unstable. They have a large amount of matter being shed, and a number of them are producing jets. And if, when they die, these jets happen to be pointing in our direction, then effectively a huge dose of gamma rays could come in our direction. Now, we'd have to be rather unlucky to be directly in the line of sight of one of these. Most of the gamma ray bursts that we see out in the universe, we just happen to be in the right direction, and if you take a large enough sample of gamma ray bursts, some of them will be pointing in our direction. We'd have to be very unlucky for a gamma ray burst only a few thousand light years away to be pointing in our direction. But if it did happen to point in our direction, the consequences could be very dramatic. It could actually strip away the biosphere of Earth. It could be an extinction level if it's to be lined up. At the moment, we think it's not, so don't worry, it's probably not going to happen. On a timescale of 1 million years, stars are going around the Milky Way. So our sun is going around the Milky Way. It's taking quite a long time to do one revolution, and virtually every other star in the Milky Way is doing the same. And they're all on essentially independent orbits. So they take roughly the same length of time to go around the Milky Way if they're at similar distances. But we are not all in lockstep. So in other words, there will be stars around us which aren't quite on the same orbit as us, and that means every once in a while we'll get close to one of our stellar neighbours. And now that we know where our neighbours are, because satellites like Gaia have mapped out the positions of stars very accurately, now that we know that, we can calculate that in the future, one star in particular, Gliese 710, is going to get very close to us. It's going to get so close it will actually enter the Oort cloud and then leave again. In other words, remember that it's not actually doing that in terms of it's not orbiting the sun. We're both orbiting around the Milky Way. So if Gliese 710 gets close enough to our sun such that it enters the Oort cloud, it's going to be a huge disruption to the Oort cloud, which means almost certainly there's going to be loads of asteroids and comets hurtling into the inner solar system because of that. The disruption, it's been calculated, will probably result in naked eye comets every month for about 1 million years or so. So huge numbers of objects are going to come our way simply because of the gravitational disruption of another in our solar system. But interestingly enough, there will be a time when our solar system will have 2 suns in it, just like other planets you've heard of. So, still on 10 to the 6. Perhaps you recognize Meteor Crater, Arizona. I'm not implying that this would happen every million years or so. This picture is there for 2 reasons. One, so that we can look at it and say, wow, wasn't it lucky it just missed the visitor center? And the other reason that's up there is to remind us that when we get meteor impacts on Earth, regardless of how often they happen, they don't last because of weathering. In other words, this might only be a few tens of thousands of years old. If it was many, many millions of years old, we probably wouldn't see it because the weathering systems on Earth, the wind and the rain, the frost, etc., would eventually get rid of very old signs of impact. And you might say, well, yes, of course, that's true of Earth, but it's not true of anywhere that doesn't have an atmosphere, like, for instance, that's not true on the Moon. Well, strictly speaking, it is still true on the Moon. In other words, the footsteps, there's Aldrin's footstep there, that will not last. That will go away, not because of the weathering that we get on Earth, but a different type of weathering, a constant bombardment of micrometeorites onto the surface of the Moon is effectively pulverizing the rock, which is why the surface of the Moon is this powdery substance called regolith. It's being pounded by micrometeorites all the time. And after 1 million years, the footprints will be gone, and it's been calculated that even the lunar lander and the lunar rover and all the other experiments that were left there, eventually they are going to go, even though nothing is happening to them other than they are being exposed to micrometeorites. So nothing lasts forever. 10 to the 7 years into the future. Pioneer 10, I said, is leaving the solar system. It's going to be passing stars in tens of thousands of years. So what's happening on a timescale of 10 million years? It probably would have passed through quite a few solar systems at this point. Remember, it's carrying a plaque that tells anybody that picks it up where it came from. The plaque says, this is us, this is how big we are compared to the spacecraft. The pulsar map on the left says, that's where we are, and we come from the third rock from the sun. So it will have been through hundreds of solar systems by the time we get to 10 million years, and 10 million years has been calculated as the point at which the plaque itself will be no longer readable. For what we said from the Moon, remember the Moon is getting pulverized by micrometeorites. Well, interstellar space is not empty, it's full of tiny grains of dust. And so if you're moving at high speed for millions of years, this plaque is effectively plowing into the interstellar medium. It's effectively getting rained on by micrometeorites. And it will get pitted and corroded to the point where it will no longer be readable. So if anybody picks this up in the first 100 or so solar systems that it flies through, they'll be able to hopefully make sense of it. If anybody picks it up after that, after, let's say, 10 million years or so, then anybody that picks it up will not be able to read that in the sense they will not be able to make sense of what we're saying about where we are and where we came from. Whether that's a good or bad idea, that's up to you. 10 to the 8 years into the future. We're now talking about 100 million years into the future. What's going to happen to Saturn's rings on that time scale? It probably helps to back off and say, well, how did they form in the first place? We don't actually know, but we are fairly sure that Saturn's rings aren't that old. They're not the age of the solar system, for instance. Some people believe that it was the result of a moon that either failed to form or got pulverized, and given the odd-looking structure of Mimas, some people are thinking maybe Mimas took a hit and the debris formed the rings. When you look at a moon like that, you might think to yourself,
that's no moon, it's a space station.
Because it does bear a certain resemblance to the Death Star there. But calculations have been done and simulations have run to say, what if you took a moon like Mimas or Mimas, forget all the other moons because they're just complicated, start with a planet with no rings, take a moon like Mimas and assume it gets pulverized by a passing comet or something like that. And then you run the simulation to see what happens. What's quite surprising is that it only takes days for a ring system to form. The debris very quickly gets spread out around the orbit. It doesn't just go round as one cloud for the next million years. It gets spread out in the matter of days. And all of the interactions between these particles, they're always bumping into each other, are such that although they would like to just go into orbit and stay in orbit, because they're all interacting with each other, they are all losing energy and slowly raining down onto the surface of Saturn. In other words, all of these particles are slowly migrating inwards. And over millions of years, you end up with the ring system that we all know and love. But it means that this ring system is dynamic. It's just halfway through its life or something like that. In other words, those particles are still on their way in. They're not in stable orbits that will last forever. And so we can run the clock forward and say, well, all of those particles are going to spiral their way inwards and then rain down onto the surface of Saturn. So Saturn's rings will not last forever. On a time scale of 10 to the 8 years, they will probably disappear. So anybody that likes imaging Saturn or looking at Saturn, get in now before they're lost completely. Whenever we think about the solar system, not just Saturn, but anything else going on in the solar system, we tend to think of it as clockwork, because we've got apps on our phone that can tell you where Jupiter's going to be tomorrow or next year or in 10 years' time or in 1,000 years' time. Or you can dial the clock back and say, where was Jupiter in 0 AD or 0 BC? But we have to remind ourselves that despite the fact that orreries and apps on our phones sort of imply that the entire solar system is clockwork, whether it be an orrery or a tellurian, we have to remind ourselves that on these sorts of timescales, the solar system is actually chaotic. We can't tell where Jupiter is going to be in 100 million years. Even if we try and measure it very accurately now, we can never measure it accurately enough to make any predictions on these timescales, because the entire solar system is chaotic. There are just too many bodies in motion, and there will always be a problem, like trying to predict the weather. You can predict the weather tomorrow, but you can't predict the weather in a month's time. It's essentially impossible because the weather is chaotic. So on short time scales, like thousands of years, we can work out where the planets are going to be. We can work out when eclipses are going to take place for thousands and thousands of years into the future. But we can't do it 100 million years into the future because the solar system effectively is chaotic. I said that the sun is going around the Milky Way. We are there on this map, which gives us a rough indication of what the spiral arms of the Milky Way look like. At the moment, I keep wanting to use the laser here, at the moment we are roughly halfway between two spiral arms. In other words, we're in a little bit of a gap between two spiral arms in a relatively low density region of the Milky Way. That means we haven't got that many neighbours. In other words, if you count the stars within 10 light years of us, there aren't that many. But things are going to change. As the Milky Way evolves, we are going to move from a relatively low density part of the Milky Way. We're going to be moving into one of those spiral arms. And the spiral arms are more densely populated with stars. That means we are going to have more stellar neighbours than we have at the moment. In other words, the number of stars within 10 light years of us is going to go up. I'm not sure exactly by how much, but it's going to go up substantially. And there are two interesting consequences of having a lot of stellar neighbours compared to what we have at the moment. One we've already sort of mentioned. For instance, when Gliese 710 comes into our solar system, it's going to perturb the Oort cloud. There's going to be loads of asteroids and comets coming our way, some of which are going to hit Earth. If we've got a lot of stellar neighbours, that's going to happen a lot more often. So in other words, there are going to be an awful lot of asteroids coming our way when we move into a spiral arm of the Milky Way. If we look at the records for extinctions of species as a function of time, this is years before the present, in millions of years, you can see various spikes. There are a half a dozen instances where there's suddenly been a lot of species become extinct, a lot of instances over the last 500 million years. It seems to happen not absolutely regularly, but roughly once every 100 million years or so. So on timescales of 10 to the 8, when we move into a spiral arm, it looks like we're much more likely to get hit by a large rock. One of these is the famous one, the last one, the KT, that is the one that killed the dinosaurs. KT is the Cretaceous Tertiary boundary, roughly 65 years ago. Just because it's 65 million and this comes around every 100 million, that doesn't mean we've got 35 million years breathing space, because these things, as you can see here, are not absolutely regular. But rocks will come our way, and there will be extinction level events when we are in a highly populous part of the Milky Way. So that, of course, is just an artist's impression of a very big rock coming our way. If you look at the left-hand side, it looks like it's heading for Italy. Okay, so bad news for Italy, but if it's large enough, it'll be bad news for the entire planet. It doesn't really matter where it hits. It'll be devastating for the whole planet, and there will be species exterminated. So far, we haven't seen a situation where 100% of species have been exterminated by an asteroid impact. But it's a question of, if there are species exterminated, will we be one of them? Well, we don't know. It's difficult to prepare for a large rock hurtling towards us. A second consequence of the fact that we'll have lots of neighbors, not only disruption and lots of asteroids, if we've got lots of neighbors, it is more likely that one of those neighbors will go supernova. At the moment, there are no stars close to us that are candidates for supernova. We have no supergiants very close to us which are massive and coming to the end of their life, which could in principle be supernova explosions. But if we end up in a part of the Milky Way in which we have many more neighbors, it is possible that one of those neighbors might be a supernova candidate, and then we might have a problem. A supernova within 100 light years of us could be a danger to Earth. So Betelgeuse out at 600 light years, not really a problem, but something closer than 100 light years, that's getting a bit much. The radiation from the supernova could be a problem. And it's been calculated that if we have a supernova within 20 light years of Earth, that would be extremely serious and could, in principle, end all life on Earth simply from the gamma radiation produced by the supernova. And if you think that sounds a bit dramatic, bear in mind it has happened in the past. We have evidence that there have been supernova not that far from Earth. Supernova within 100 light years or so have left signatures on the Earth. Supernovae generate lots of exotic elements that don't exist naturally on Earth. One of them is called iron-60. It's an isotope of iron. And we know that that particular isotope doesn't last very long. In other words, when we look at that isotope, we see that it's radioactive and it decays or changes into something else. So that particular isotope of iron changes into cobalt and then nickel after a few million years. And yet we have found that element in certain sediments in Earth. If it only comes from supernova, it's not naturally occurring. It hasn't been there since the Earth was formed because it only exists for a few years. Then if we find it on Earth, it must have arrived in the last few million years or 100 million years. It hasn't been there for the last 4 billion years waiting for us to find it. It's arrived relatively recently, and we think the most likely origin is from a supernova not that far away from us. So supernova have gone off close to us and will do again when we next move into a spiral arm of the Milky Way. I'm coming back to the spin of the Earth again. It's an interesting clock in itself. For the last 100 million years on this time scale, the Earth has been slowed down by the Moon. The Moon is tugging on the Earth is tugging on the Moon is slowing the Earth down, and the Moon is moving away. In other words, the Moon is robbing the Earth of some of its angular momentum. So the Moon's orbit will increase. The length of the day will slow down. We said before that we had to add leap seconds. Well, now the length of the day is 25 hours. Adding leap seconds just doesn't cut it anymore. You may as well decimalize your day and forget the idea of 24 hours and move over to 100 hours or 25 hours or something like that. So regardless of what we do with our clocks, we have to think about what's the consequence of the moon taking some of the Earth's angular momentum and increasing the size of the moon's orbit. At the moment, the moon is moving away from us at about 3 centimeters per year or so. We can measure that and have been doing essentially every day since Apollo astronauts landed on the moon. We've been measuring that distance and watching it increase a few centimeters every year. But by this time in the future, 100 million years into the future, the distance from the Earth to the moon will be large enough to the point where we will no longer be able to see any total eclipses of the sun. In other words, the moon's apparent size in the sky, because of its distance, will be so small, the best we can hope for is the sort of annular eclipse that we had a little while ago crossing the United States. So we can still get partial eclipses and we can get annular eclipses, but the moon will never be big enough to cover the entire disk of the sun as of this point onwards. Bit of a shame. So again, any eclipse chasers, get in now before this happens. A more serious result of the moon moving away from the Earth, it's a bit of a shame we never see that again, but one of the consequences of the moon moving away from the Earth is at the moment the moon is a very stabilizing influence on the Earth's axis. So in other words, the tilt of the Earth, 23.5 degrees roughly speaking, the tilt or the obliquity is stabilized by the moon. If we look through the historical record, we believe the Earth has been about 23.5 degrees and hasn't changed by more than about a degree over the records that we can see in the Earth. And that little cartoon on the left shows you how much that is. It's a tiny little change from about 22 degrees to 24.5 or something like that degrees. But if the moon moves further away, it no longer stabilizes the axis of the Earth, and the Earth's axis can then do whatever it likes, and it will be perturbed by all of the planets and pulled on by the sun, and the Earth's axis will no longer be stuck at 23 degrees. It's been calculated that if the moon is something like a quarter as far away, in other words, 125% of its value, then the tilt of the Earth could change erratically. And of course, if the tilt of the Earth changes, then the seasons go out the window completely. The only reason we get stable seasons is because the Earth's axis is stuck at 23 degrees. If it could go vertical or horizontal, such that one pole pointed at the sun, for instance, then the idea of seasons just gets completely trashed. So again, the Earth's climate, once the Earth is no longer being held, if you like, by the moon in terms of stability of its axis. I said that Pioneer is leaving the solar system, and after 10 million years it won't be possible to read its plaque anymore. Voyager is also leaving the solar system, and it contains a gold disc with recording of speech and music and a few other bits and pieces. The disc on Voyager won't be readable after 1 billion years. Why is it so different? Is it the metal it's made of? Well, not so much. The reason that Voyager's disk is going to last substantially longer than the plaque on Pioneers 10 and 11 is that the disk, which contains the music and the words of welcome from various world leaders, etc., that disk is being protected by a cover. In other words, they had the good sense, rather than put a disk and have it face the interstellar medium as it goes plowing through, they put a cover over the top to protect it. Great idea. So the cover is going to get pitted and corroded and etched and be completely unreadable fairly quickly, but the record itself will survive 1 billion years, it's been calculated. The catch is the cover contains the instructions for how to read the disk. So you would hope that, okay, Voyager is going to pass through thousands of solar systems by the time it gets to this particular point. If it's been through 1,000 solar systems and then somebody picks it up, even if they can't read the cover plate, perhaps they're intelligent enough to figure out how to get the information off the disk and listen to the words of welcome and the Beatles music and everything else that's on the disk itself. We are still 10 to the 9. We are still 1 billion years into the future. The sun has not yet changed into a red giant, which it will do, but it's on the way. It's starting to change. It hasn't yet run out of fuel, but it is changing its luminosity. They reckon it'll change its luminosity by an increase of something like 10% every billion years. And that might sound very slow, but of course 10% and then 20% and then 30%, that means it's going to get rather intolerably hot on the Earth. As it moves towards the red giant phase, it will continue to increase its luminosity. And it's been calculated that after a few billion years, the Earth will reach something like 80 Celsius. In other words, the oceans will start to boil dry. So we have to find something to do. We either have to, even going underground, it's not obvious that will necessarily help. So we have to find some way of dealing with that. Perhaps we leave Earth till it cools off a bit and then come back again. So the sun is going to become a red giant. It's going to swell and its diameter is going to increase. And the surface of this red giant is going to get quite close to the Earth. And you think to yourself, that could be a problem. And it's often said that the sun is going to swell up into a red giant until that red giant has a diameter larger than or at least as large as the orbit of the Earth. Well, that's true, but actually it's not clear whether or not the Earth is going to get engulfed by the sun or not. The jury is still out on this one. And that's because although the sun is going to expand, as the sun expands and goes into its red giant phase, there's going to be a very strong solar wind. There's going to be a lot of matter leaving the surface of the sun. So the sun is going to get a little bit lighter. And if there's less gravity pulling on the Earth, that means the size of the Earth's orbit is going to increase. In other words, the Earth is going to drift away from the sun. And if we have a look at the cartoon on the left, not to scale, we can see that as the sun expands towards red giant, the Earth is actually going to move away from the sun. So yes, the sun will probably end up the size of the original Earth orbit, but the Earth won't be there anymore. The Earth will actually be further away from the sun. Perhaps the Earth is going to be somewhere where Mars is now, for instance. That's a possibility. The calculations aren't easy to do, and there's lots of other effects that need to be taken into account. So people are on the fence as to whether the Earth will be engulfed by the sun or won't be engulfed by the sun. Let's assume optimistically that the Earth survives this particular red giant phase. Once the sun has gone through its red giant phase, the sun will turn into a white dwarf. We're not too sure what's going on in the middle of a white dwarf. It's probably very dense carbon. It could even be diamond, who knows? So there could be a diamond the size of the Earth in the core of the sun by the time the sun has gone through its red giant phase. But the Earth will have a problem after the sun has gone through red giant and then into the white dwarf phase. And that is the Earth is going to lose its magnetic field. The core of the Earth is going to cool down, and when it does, it's going to lose its magnetic field. The core of the Earth is not being kept molten by the sun. The core of the Earth is molten and will stay molten for quite a while because of radioactive elements in the core. The radioactive decay is producing energy which is keeping the core molten. Regardless of what the sun is doing, those radioactive elements will be decaying away, and eventually they will not produce enough heat to keep the core of the Earth liquid. So the core of the Earth is going to solidify. If you don't have a liquid core spinning, you don't have a dynamo, you don't have a magnetic field. So the Earth is going to lose its magnetic field, and when it does so, that means cosmic radiation is going to be raining down onto the surface of the Earth. And the Earth will, if it hasn't already lost it, it will lose its atmosphere. It is thought by a number of people that that is possibly what happened to Mars. Mars is smaller than Earth, and it will have had a solid core before Earth gets a solid core. In other words, Mars's core might have been molten at one point, but Mars's core has solidified because it's a smaller object, it loses heat faster, and as a consequence, Mars lost its magnetic field, and perhaps because of that, Mars lost its atmosphere, or at least a dense atmosphere, and it's only got a tiny nebulous atmosphere now. They say bad news comes in threes, so okay, if we survive the sun going through a red giant phase, if we survive the loss of our magnetic field, what's the third one that's going to come along? Yeah, Andromeda is just waiting to crash into us, basically. So on a similar time scale, soon after the sun runs out of fuel, Andromeda galaxy is going to come crashing into us. Actually, this is the least apocalyptic scenario, because when a galaxy collides with another galaxy, probably no stars hit each other. If the sun gets dragged out of the Milky Way, the planets will just go with it. So in other words, it won't necessarily change anything about our solar system. So on this sort of timescale, a few billion years, the Andromeda Galaxy is going to pass through the Milky Way. There's going to be an absolute riot of new star formation because all of the gas in one is going to plow into all of the gas in the other, and all of the dust is going to get shaken up. The stars won't give a damn, but there'll be a whole load of new stars generated when these two galaxies pass through each other. The Andromeda Galaxy will pass through, and then the neutral gravity will probably bring them back again, and eventually they will settle into one sort of mega galaxy, if you like. And you possibly can't see it here, but this particular indication of what it might look after 5 billion years is most of the stars will have settled down into this one large galaxy, but there might still be two nuclei, the old nucleus of the Andromeda Galaxy and the old nucleus of the Milky Way. There's supermassive black holes at the core of each galaxy. They will probably end up orbiting each other, and it will take them quite a while before those two supermassive black holes coalesce into one even larger black hole. What we call this galaxy, we don't know. We can't call it Milky Way anymore. We can't call it Andromeda. Andrilke, Milkdromeda. We'll have to find a name. We've got 5 billion years to find a name, so I'm sure there'll be a competition at some point. So not really a problem. After 10 to the 11 years into the future, the dance between the Earth and the Moon finally stops being a dance. At this point, the Moon will have taken essentially all the angular momentum it can from the Earth, and now one day is the same as 1 month. In other words, the length of time it takes the Earth to rotate once on its axis is now the same as the length of time it takes the Moon to go around the Earth. So the day is now much longer, and basically what we used to call a day, the rotation period of the Earth, is now equal to the orbital rotation period of the Moon. So the Earth is now tidally locked to the Moon. In other words, the same face of the Earth always faces the Moon. So you can imagine if you were standing on one continent on Earth, the Moon would be in the sky and it would be fixed in the sky. Just like the Earth is fixed in the sky for Apollo astronauts standing on the surface of the Moon, the Earth doesn't rise or set. So similarly, if you're on Earth, the Moon will be fixed in the sky. If you're on the other side in a different continent, the Moon will never rise above your horizon. So that, of course, is mirroring what the Moon has been doing for billions of years, because the Moon has been tidally locked to the Earth for ages. Eventually, the Earth will be tidally locked to the Moon, and they'll be always facing each other, much like Pluto and Charon do at the moment. They're always the same faces facing each other. Once that happens, there's no more angular momentum interchange, because the only reason one robs the angular momentum of the other is if they're spinning at different rates. So once they're spinning in lockstep, as it were, there's no longer any angular momentum switching between them. The Andromeda Galaxy is going to go ploughing into the Milky Way. The Milky Way has actually got lots of little neighbors, lots of dwarf galaxies, tiny little things buzzing around it. And if we look at the local group here, we see that we've got the Milky Way there, and we've got M31, the Andromeda Galaxy, and M33, the Triangulum Galaxy, and loads of these smaller galaxies. Not only will Andromeda collide with the Milky Way, all of the galaxies in the local group will end up in that central galaxy. It won't be a spiral, it'll probably be some rather large, messy, elliptical galaxy. But instead of having hundreds of members of the local group, there will just be one, because effectively galaxies are cannibals and will eat each other. What's going on with galaxies on scales much larger than the local group? Well, we know that it's possible, for instance, to image galaxies, even very remote galaxies. For instance, during lockdown, I imaged a galaxy that's receding from us because of the expansion of the universe at something like twice the speed of light. So we know that we can see nearby galaxies, and we can even see galaxies that are receding faster than the speed of light because of the way the expansion of the universe works. So we know that's possible. But if we have a look, for instance, at the Hubble field and remind ourselves that the Hubble is looking at, by doing long exposures, looking a long way in space, in other words, looking a long way back in time, the Hubble can see huge numbers of galaxies. Some of those might be close enough that they are receding at less than the speed of light. Many of those dots there will be receding at very high velocities. And it's sobering to realize that on a timescale of 10 to the 12, the expansion of the universe, which is, if it continues the way we think it's going to continue, objects will be receding from us so fast, it will be impossible to image them. In other words, even if we had a Hubble Space Telescope, in 10 to the 12 years' time, if we took a Hubble Deep Field, we would see no galaxies, because they would all be too far away because of the expansion of the universe. We would only see the stars that are part of our own galaxy. And in that previous image, there were 2 stars and everything else was galaxies. And again, it's sobering to realize that if a civilization comes into existence in 10 to the 12 years' time, if they build themselves the equivalent of a Hubble Space Telescope, it doesn't matter how good their telescope is, if they point it out into the universe and say, what sort of universe do we live in? They will come to the conclusion there's nothing out there other than the stars in their own galaxy, because they will not be able to see anything beyond that. We live, in a sense, at a special time where we're able to see trillions of galaxies in the observable universe. That won't always be the case. There will come a time when they are simply not visible. And no matter how intelligent a future civilization might be, they will not be able to observe those galaxies beyond their own. I said in the beginning of everything that it took 3 minutes to make all of the hydrogen that fuels everything that we understand about stars and galaxies. After something of order 1 trillion years or so, the hydrogen is almost all gone. It's all been used up. So there'll be no new star formation, or at least we think there'll be no new star formation. Some people have some crazy ideas. Some people have said, well, there's no proof, but what if? What if you don't make stars out of hydrogen, you make them out of something else? We don't know how to do that. We think all stars are made out of hydrogen, and then they start making heavier elements. But some people have said, well, is it possible to think about stars that are actually made out of heavier elements rather than the lightest element, hydrogen? And some people have said, well, maybe it's possible that you can actually get a star made out of heavy elements that has nuclear reactions occurring at the core, but the surface temperature is very low. A red giant might have a surface temperature of thousands of Kelvin. What if it's 10 times colder than that? It might have a surface temperature of hundreds of Kelvin, or conceivably 0 Celsius. Is it possible to make a star with nuclear reactions at the core, but ice in the atmosphere? In other words, frozen stars. And if when I say frozen stars, you tend to think of Disney, and you think of Disney Frozen, for those of you with youngsters in the family, that's not what I'm talking about. So if that's what's in your head, let it go, because what I'm actually talking about is nuclear reactions in the core and ice in the atmosphere. It's highly speculative, and loads of people say this is rubbish, but it's an interesting idea that can you make a star colder than the sorts of stars that we see today? But that's really just an aside, because before we can make any sense of what happens next, we need to think about what the universe is doing on the grandest of scales. In other words, if this picture shows us how big the universe is, there are 4 colored lines, because there are 4, more than 4, different models of how the universe might behave. The horizontal line here is the age of the universe, with now in the middle there, and the vertical scale is the relative size of the universe. We don't have to worry about the actual size, it's just relative to where we are at the moment. So there's us now. So now the universe is of size 1, and you can see that it is expanding. We're not sure exactly how it's going to behave. If you look backwards in time, when was it size 0, if you like? Well, that depends on which particular colored line you think is the one that actually describes the universe in which we live. And each of those colored lines say something different. For instance, the orange line says, well, orange means if we live in a universe which has got a huge amount of matter in it, well, that means that gravity is eventually going to win. Because if you've got a lot of mass, that means gravity is very strong, And as the universe is expanding, gravity will eventually slow that expansion. The universe will stop expanding, and then it will start contracting again. So that's why the orange originally goes up, but then it curves down, and you end up with a big crunch when everything comes back to zero again. That's the so-called closed universe. That was a popular idea some time ago, but there's plenty of evidence that says, no, that's not the universe in which we live. When we look to see how much mass and how much energy is in the universe, we don't think we're on the orange curve or even the green and the blue curve. Our best guess from what we can see at the moment in terms of how much matter and how much energy is out there, we think we're on the red line. Now, to start with, there's not much difference, but eventually you can see the red line looks very different from the other ones. The expansion will continue. The size of the universe will continue growing indefinitely, no matter how far we take this graph to the right. Not only is it growing indefinitely, but look at the slope. It's getting steeper and steeper and steeper. We're not sure if that's going to continue. At the moment, the evidence is that the universe is expanding, and it looks like the expansion is accelerating, and we cannot see any reason why that's going to change. At the moment, we're simply assuming that's going to continue the way it is. But of course, we could discover something next year which completely changes that idea. But at the moment, I'm going to assume that the universe is not going to end up in a big crunch, but is going to continue expanding forever, because that's what the evidence is telling us at the moment. Now, in order for this talk not to go on till midnight, I'm going to change the scale at the there. Instead of each box, each red triangle, each red rectangle moving along being 10 times further into the future, we're now going 1,000,000 times further into the future every time we change one of our boxes. So in other words, we're talking about 10 to the power 30, which is a zillion years, I don't know. 10 to the 48, gazillion, I don't know. There's no adjectives. There's no useful adjectives once you get above sextillion, septillion, nonillion, octillion, decillion, etc. You start ending up with really silly names. So where did we get to? Before we took this little diversion and said, is the universe going to end up in a crunch or is it continue expanding? Let's assume it's going to continue expanding and continue the story. We left it with the universe made all the hydrogen in 3 minutes, but the hydrogen is running out. Stars might live for trillions of years, but they don't live forever. So what does that mean? The age of starlight will come to an end. There will be a day when there are no more stars shining. When the age of starlight comes to an end, when all the hydrogen has run out and you can't make any more stars and the last long-lived star has died, well, they will still be floating around. The dead stars, no longer shining because no longer nuclear reactions generating starlight, they will be drifting through space like zombies. We'll still have dead remnants of stars, white dwarfs, neutron stars, black holes, for instance, none of them undergoing nuclear reactions to keep them shining. So even white dwarfs, for instance, they might start off quite hot because they were made hot, but they will cool off. They will simply cool down, and white dwarfs should end up being called black dwarfs. And even if we try to see what's on the surface, it's just effectively dead matter. It might mainly be carbon, it might be something else, but it's effectively just atoms that are not emitting any light because there are no nuclear reactions going on anymore. Some stars might be ejected from their host galaxies. Any that aren't will probably be eaten by the supermassive black hole that's at the core of every galaxy. Perhaps every big galaxy, but a lot of people are now thinking that every galaxy has a supermassive black hole at the center. and that will effectively hoover up all the stars in the galaxy once they are dead. We think that any matter, including stars, will get funneled into the supermassive black hole by following magnetic field lines. They've been mapped out in a galaxy called NGC 1097 by SOFIA. SOFIA is the Stratospheric Observatory for Infrared Astronomy. That's the one with a telescope in the back of a 747. Recently decommissioned, so watch out on eBay. Might be up for grabs if you want a telescope like this. But they have mapped out the magnetic field lines in this galaxy, and this seems to indicate, although it's rather complex, that these magnetic field lines are acting as tram lines, as funnels for the matter, and it's effectively allowing the supermassive black hole at the center to feed. It might be the same in other galaxies, but more research needs to be done there. What happens to all the atoms? Well, we know that atoms are protons and neutrons in a nucleus and electrons buzzing around the outside. But there's actually, on this time scale of 10 to the 36 years, there is not a clear message as to what's going to happen to these systems. We think protons and neutrons and electrons as atoms are stable. Neutrons themselves are not stable, they will decay, but when they're in a nucleus, they tend to basically last forever. But the protons, the positively charged particles in a nucleus, some people think they might decay, they might change into something else. And if they do, that means every atom in the universe will fall apart. We're not sure how long protons will last, no less than 10 to the 36 years, but no one really knows what happens after 10 to the 36-ish years. So the timescale is uncertain. It's very difficult to extrapolate from experiments we're doing now so far into the future. But it will have a consequence if protons are not stable particles, because atoms will disappear. But even if we assume they don't, atoms won't last forever anyway, because neutron stars don't contain atoms, black holes don't contain atoms. The only atoms in the universe at this point are in white dwarfs, and eventually they are going to evaporate via a process I'm not going to describe. So eventually atoms will disappear on timescales of order 10 to the 42 or so, and therefore we're left with a very interesting universe. Interesting or boring, depending on which way you look at it. There will still be black holes, and black holes will merge. Much like I said earlier, galaxies are cannibals. They will merge with each other, just like we are going to merge with the Andromeda galaxy. The supermassive black holes at the core of those galaxies are going to merge. That process will continue into the far, far, far future. So supermassive black holes are going to grow from millions of solar masses to billions of solar masses, and there's no reason why they don't keep growing until they are trillions of solar masses in mass, absolute monsters. But even though they will grow for a long, 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 long time, holes do not last forever. They are not eternal. Black holes, as best we can tell, evaporate as long as you wait for a really long time. This has not been proved yet. It was a hypothesis of Hawking, Stephen Hawking. A lot of people think it's pretty much right, but we have no direct proof of it yet. So why do we think they evaporate? Well, it's a quantum mechanical effect. Let me just give you a very brief idea of what we're talking about. It is possible to borrow and take something from nothing. Let's face it, that might be how the universe came to exist in the first place. You are allowed to borrow from nothing and use it to do something. You can borrow from nothing and use it to make, for instance, particles and antiparticles, which will then annihilate and pay back the loan. In other words, you take some energy, you make some stuff, the stuff makes some energy, and you're back to square one again. That process is a quantum mechanical process which, as far as we can tell, happens all the time and might conceivably explain the origin of the universe. But here we're trying to use it to understand why black holes evaporate. And what Stephen Hawking calculated in a rather more complex fashion than the cartoon I'm showing here, what happens if you borrow some energy and make particles and antiparticles just outside a black hole. So if we imagine that's the event horizon of a black hole, what if just outside the event horizon you borrow some energy and you make stuff and anti-stuff, and one of them falls into the black hole but the other one doesn't? Now you've left yourself with a black hole, and it looks like it's emitted something. It looks like something has come out of the black hole. Strictly, it's come from the event horizon of the black hole. But it looks like it's emitting something. It looks like there's a flux of something, particles or radiation, coming from the black hole. And that's what we now call Hawking radiation. Hawking calculated that the radiation increases with decreasing large object. Hawking radiation is very, very, very small. And as the object gets smaller and smaller and smaller, the radiation gets higher and higher and higher intensity. So there's this sort of avalanche effect. As it gets smaller and smaller, it will disappear in a flash. So at first, the radiation levels will be very small, but they will increase as the black hole evaporates until it disappears in a flash of radiation. But notice the scales here. We're getting really into the high numbers here. We're talking a long, long, long way into the future. Evaporate very slowly. So a supermassive black hole that's a trillion solar masses is going to take ages to evaporate, but it will evaporate eventually. Even these monsters of galaxies will eventually evaporate, but they will take trillions of times longer than the sort of black holes that are sort of stellar mass. So are we talking about the end? And that occur? I've got to the end here. I had 10 to the power 84 as my last box. Strictly speaking, that's not quite enough. But that number is about as big as we want to go. 10 to the power 100 is a Google. Not that one. That's a misspelling of the real Google, Google with an OL on the end. 10 to the power 100 is a Google. And after a Google years, it's been calculated that according to the laws of physics as we understand them in the moment, after 1 Google years, the last black hole will have gone. And there will be nothing left in the universe other than some radiation floating around. So at this point, after this point, nothing interesting happens whatsoever. The universe will continue to expand. The radiation that's floating around will get stretched to longer and longer and longer wavelengths, but there's no matter anywhere, and therefore nothing happens, and so you could argue that time becomes essentially meaningless. If there's nothing in the universe to happen, then how will you be measuring time anyway? So nothing interesting happens beyond a Google years. Mathematicians can do calculations beyond that, but I would argue it's not very interesting. I don't normally the end of numbers, but just to remind us how stupid a number 1 Google is, there it is in full. So 1,000, a million, a billion, a trillion, a quadrillion, etc. You can see that Google is 100,000, million. It's just silly. But that just reminds us that you can still do calculations on those timescales and calculate how long it takes to black holes evaporate, and you get numbers that are comparable to that sort of number. Is this the end? Well, virtually, yes. Eternity is a very long time, especially towards the end, as Woody Allen once said. But to try and put it back to some sort of meaning, I quite like the quote from XKCD, which is a comic that involves sometimes astronomical themes. And they said, to put it in a human perspective, a human is simply a system for converting dust billions of years ago into dust billions of years from now via a roundabout process which involves checking email a lot. I thought that was a very interesting way of getting the human perspective on this whole thing. Okay. That's a rather depressing thing to say, that after a Google years there's nothing left and the universe becomes absolutely boring and nothing happens for the rest of time. Let me finish with a little epilogue. I believe that we live, in a sense, in a golden age because the sun is middle-aged and well-behaved, and the moon is at just the right distance to stabilize the Earth's axis and hence stabilize the seasons. And as a bonus, it also is just the right distance to give us a total eclipse of the sun. And thanks to evolution, we have been able to explore and discover, and perhaps more importantly, understand the universe. And we've done that by visiting our closest neighbors in the solar system and building equipment and telescopes that allow us to see that the observable universe is full of trillions of galaxies at distances of billions of light years. Humankind could not have existed in the early universe. We needed generations of stars to make the heavy elements, to take hydrogen, make helium and carbon and phosphorus and iron and all the other elements that we need to make life, at least life as we know it. We could not have evolved to be who we are in the early universe because we needed those generations of stars to make the elements. And we've just seen that in the future, things are going to get very dark and very boring. So you could say the best time to exist is now. Thank you very much.
Well done.